know that how fresh snow looks like. It is much more white, and we already know why this is so white. And as it goes through the process of metamorphism, its albedo is also reduced. And we already know why that albedo is reduced, essentially because the trapped air between the ice crystal is removed because of the compaction, as well as there is the presence of mineral dust on the surface and some amount of increase in grain size, either due to melting snow or due to metamorphosis. So all these processes make snow reflector slightly reduced, and it further reduces when we remove the all trapped air between the two ice crystal, and it gets converted into ice, and which has much higher density, and its reflectance is further reduced. We know that. And some other contaminants can also significantly reduce the albedo of snow and ice if there is a volcanic ash or if there are debris covered on the glacier. That can also significantly reduce the snow albedo. So snow albedo would have a wide range coming from very high, it's almost 90%. In case of fresh snow, it can, as it goes, it's 60 to 70% when it becomes a dirty snow or old snow. It can go up to 40% or 30 to 40% when it comes converted into the ice. We are talking here about visible and near infrared part, and it further reduces if it is covered by debris cover or some sort of volcanic ash, making it a very wide range. But it is also important for us to understand why we study snow cover in Himalaya. Himalaya has a large distribution of seasonal snow cover, and we already know that globally also there's a large seasonal snow cover distributed. And as summer and spring comes, that seasonal snow starts melting and producing water to the numerous streams originating not only in Asia, but also other parts of the globe, whether it is North America, South America, or in Asia or Europe, all those places, seasonal snow contribute quite significantly. Whenever it comes to the Himalayas, it has very large spatial distribution. It means in winter almost 1.6 million square kilometer area is covered in the Hindu Kush Himalaya, and its variability is very large. That means it is 85% in middle of winter and only 10% at the end of summer. So it is really huge area. Is changing over a period of 6-7 months. So it is from February to June, July, August, February to August. It is almost 3-4 months. It is 85. So 75% of geographical area is reduced, and it is really a major contributor to the snow, to the numerous streams which are originating in the Himalaya. Therefore, it is important for us to understand how to monitor seasonal snow cover. There are different ideas to monitor snow cover are there. But generally, people have used visible and near infrared or shortwave infrared radiations to measure the to develop an algorithm so we can map the seasonal snow cover. That's the idea. So we will try to understand how when algorithm was developed by using AVIF data. We will move on to that part later on, where basically we have visible and near infrared and squeeze band, and it doesn't have thermal band. So it introduces certain limitation on what we can do. But first let us understand what is the meaning of algorithm. See, algorithm is nothing but method expressed as a finite list of well-defined instructions for calculating a function. So there are set of instructions which we give. They are few in numbers, not necessarily few, but they're finite in numbers, and so that we can calculate a function. And in this particular case, function is a snow cover. So essentially what it means is that we should separate between the snow pixel and other pixel. That's the idea in algorithm. Uh, so this also means that this instruction should be unique so that it can estimate the snow from other land features such as vegetation, rock, soil, and water. So these are the common features you can see into this snow cover area. And we should be able to identify a snow pixel from these pixels. So we can use, if you want to extract the snow, you can use the one band or combination and band, and which has a very unique range. That means we are confident that this is only that. But key question is when we receive a satellite data, which is given in terms of digital number, because that is how satellite data is written. So key question is whether we can use the digital number or not. That's the idea which one should understand. But just think over it, and then we will move on to that. So first thing we have to understand that if we want to give a finite instructions and a unique unique reflectance properties, then we should look into the spectral reflectance curve uh, of a snow, vegetation, land, ice, or a wavelength for which satellite data acquired. And that is very important that it is because there are a lot of engineering limitations on we can have very ideal requirement, but when you send a satellite in space, there's a compromise on multiple requirements. So we have to do on whatever we are given. So we have look into the reflectance curve. So here you can see that this is the reflectance of snow is high in visible region and low and NIR region. So if you look into the visible region, which is around this region, and NIR region is around 700, beyond 700 nanometers. So in this part of electromagnetic spectrum, you can see that reflectance is very high of snow. And if you come into the sphere part of electromagnetic spectrum, which is 1350 to 1550, in this part of electromagnetic spectrum, the reflectance is very low. If you look into the other land features, like soil, if you look into the soil, soil is low in visible part of spectrum, and it is very high in a sphere part of spectrum. And this is also slightly different, which has relatively low reflectance in visible part of spectrum, and it has slightly higher reflectance in sphere part of electromagnetic spectrum. So snow has very unique spectral reflectance characteristic where you can see that it has high reflectance in visible region and low reflectance in this region. So if it is so, then how that snow should look on a satellite images. So this is a WIF satellite images, which is taken in visible part and the sphere part. So previous slide, we have seen that visible part has high reflectance. It should have very high digital number or should have high reflectance, and sphere band should have low reflectance. So if you look into this, you can see that snow appears white on visible part and snow appears almost, black in sweet band. Uh, so, so satellite images are showing, which is very uh, uh, following the reflectance curves which we are shown, which we are developed in the ground, and this is from satellite. So these are two different platforms and two different instruments by which the observations are done. So we know that now we are something very unique. Another classical way of doing a remote sensing is either give a scatter plot. That means you identify the land features, which you are confident this is the land feature. So you identify some clouds on satellite images, you identify snow on satellite images, you identify ice, then you identify rock, you identify rock under shadow, you identify snow under shadow. So all those things you can do it. So when you plot it on scatter plot between, this is a scatter plot between green and sweet band. So what you can see is, so what essentially you can see, is that uh, there's a lot of space between the cloud, between snow, and in mountain shadow also you can identify some features. So, but they are like rock and snow in mountain shadow is very close, and there is not enough space. Then snow under shadow is also a very close space. So, but it is indeed possible if you use just spectral reflectant characteristics for you to identify snow. However, it will be very difficult for you to identify snow under mountain shadows because they are confused in mountain shadows has very low radiances and making it very difficult to detect it. So that is how if you look into the satellite images. So one of the difficulties, if you use only spectral reflectance curve or spectral reflectance data, that means digital number or reflectance, then some of the features, no features, which are under mountain shadow, you may not be able to identify. That is the one problem which we have seen in this figure. So let us look into what more we can do in order to identify snow under various categories. So let us look in terms of characteristics of AVIF sensor, which is IRSP3, and of course AVIF sensor is still there, and I don't think there is a characteristics have significantly changed. So it had 56 meter at nadir and 70 meter off nadir. If you have really nadir means vertically down, and if you have 700, and if you can look into the swath, which is 740 kilometers. So nadir is vertically down, and the far end is 320 kilometers, 320 kilometers this side and 320 kilometers this side. So at the end of 320 kilometers, you will have 70 meter is a ground sampling distance. That means it is a special resolution, it is 70 meters. In the far end and at the center, it is 56 meters. But what you essentially do is you try to resample the data, and then at the end you get the 66 meter. You can do the spatial resolution. So it has SWAT 704, and it has four bands: band 2, band 3, band 4, and band 5. You must be wondering why there is no band 1. Because band 2 is in green, then this is in red, this is in real infrared, and band 5 is a sweet band. But there is no band 1. But conventionally, band 1 is reserved for blue, region of electromagnetic spectrum. So if you don't have blue band in a satellite, you just start naming it from. So conventionally, moment you say band 2 means people will think it is in green band. Band 1 means blue band. Band 3 means red band. So that is how conventionally those who are working in this field. Yeah. The level of quantization 10. Uh, you know how much will be digital number if 10 quantization is there. So um, you can just find out. So, but what is this radius setting? So it is, radius setting is milliwatt per centimeter square per steradian per micron. So historically, the radius settings is kept a little bit lower. We will come to that, why that was kept lower. And that is also because the data was, because of the some engineering restrictions, so because of that, data was also not of 10 bits, but it was 8 bits or 7 bits. So that means you have less number of digital numbers. So here in this case, it is 100% albedo. What it means? It means that uh, in a horizontal plane, uh, then how much is solar radiation is coming uh, in this is a 53. So in a band 2, that is green band, is a 53 milliwatt per centimeter square per steradian per micron. That is how you receive the radiation. So even if satellite reflects 100, the land reflects 100%, then sensor will not get saturated. That's the idea. But that does not mean sensor will not get saturated. It will get saturated if we will discuss that issue later on. So if you look into the historical um, uh, sensor building exercise, and this was done in 2003, designing was done in 2000, and then it was satellite data was available from 2004. So it is a substantial improvement, even though that improvement is not enough to not to saturate satellite sensor under snow condition. So we will see that why really happens. And then there is a band-to-band registration is also there is some how much pixels, so 0.25 pixel will be error if you take the one band to two band. They have to superimpose on each other correctly, band 2, band 3, but there will be some shift and the tolerable 6 is 0.25. That's the idea of this spectral characteristic. So if you have now this idea that then the concept of normalized snow index was used to monitor the seasonal snow cover. So what is the normalized snow index? It is something which is reflectance in band 2 minus reflectance in band 5 divided by reflectance in band 2 plus reflectance in band 5. So why do we use this? Band 2 and band 5, we already know that. We use this band because reflectance is very high in band 2 and reflectance is very low in band 5. And then you can normalize it. And the advantage is normalization is you can have a definite range of NDSI. That means it is from -1 to +1. That is why you really work on small numbers. And that is the idea by which this is done. So it is normalized difference snow index, where we use the band, one is high reflectance, one is low reflectance. So this is the idea to do that. So key question is, what are the reflectances? This work is done in Dhundi Observatory in Himachal Pradesh. So you have now different land features. Here you can see that pine, deciduous forest, wet snow, highly wet snow, water and cloud. So these are the land features and which you have various band 2, band 3, band 4, band 5. These are the bands of A bits. So what you do is you take the spectral radiometer into the ground and try and get its reflectances. So you can see here the pine has very low reflectance. Then deciduous forest has low reflectance. Wet snow has zero point 0.8 difference. No, as it becomes very high, very wet, it reduces further to 0.76. It water, it is substantially low, and cloud is little bit high. So when you do it, then you have band 2, then you have band 3, band 4, you can see here. So what you can see here is a band 5. And if you come into the wet snow here, band 5 has very low reflectance, 0.041, and it has very high reflectance in 0.82. In a pine, in a vegetation, it reverses. So it has very low reflectance in band 2, but it has very high reflectance in band, not very high, but higher than band 2 in this. So, and if you can look into all those features, so you can see here is that when it comes to the pine and deciduous forest, it has very negative NDSI, and it is wet snow, very wet snow, water. They have very positive. So reflectance, and you see that the reflectance between snow and water is, or NDSI between snow and water is very close. It means that if you use the NDSI technique, you will not be able to differentiate between the snow and water. So that is the limitation of this technique. You should be quite aware of it. And then the cloud, which has slightly different reflectance, which is also positive, but much more lower than snow and water. But it depends upon the nature of cloud. We will visit that issue sometime later on. So that is the idea. But when you look into, even though on ground it is very clear, when it comes to the satellite, it is not necessary that you will only get energy which is reflected from the ground. So there are a couple of other things also happen, because there is interaction of incoming solar radiation with reference to atmosphere. So what will happen is when solar radiation comes, some of that radiation can get attenuated within the atmosphere, and that is because of the presence of um, mineral dust or aerosols, make it scatter, and some of that energy will come, and some of that energy come in the form of direct solar radiation, and some might come as a diffuse radiation. So what happens is some of the radiation which is scattered by the atmosphere can straight away go into the sensor. That possibility is also there. So what will happen is, and when energy which is reflected by the surface, and it will depend upon the reflectance characteristics, and it depends upon BDRF. What is the BDRF? It's a bidirectional reflectance function. It is a mathematical description how reflectance varies for all combination of illumination and illumination viewing angle. So we were looking in terms of, we will see some of that issue later on, but depends upon the sun-earth geometry and the local illumination angle, local topography, bidirectional reflectance function will change. And it is accounted for. So depending upon that, energy will be reflected back into the atmosphere. Some of that energy will transmit and go it, and some of that will be scattered into the atmosphere. So the energy which is received, which is a part of transmitted energy and part of energy which is coming from path radiance. So that can produce sometime the issues of we need to now remove the energy which is coming from the atmosphere so that we can get the understand better the reflective characteristics of the ground. That's the idea. So in order to do that, first thing we need to do is convert the radians, uh, uh, digital number into radiances. You have already done that exercises and you know that how to do it. That means mm, you have a slope response function and intercept by using this whichever calibration characteristic available when that satellite in the ground in the laboratory, they have done the calibration, and by using that calibration you can do it, or you can do the calibration when it is in space also by using some of the features such as Amazon forest or some desert in Thar desert, where the reflectance doesn't change quite significantly from place to place because of the huge cover of vegetation canopy in Amazon or huge cover of desert. So there's no moisture and so many other things are not there. You can use such land features and then calibrate it. So you can calibrate it and convert it into digital number. You have done that exercise, so I will not go into detail of that. Now you can also once you have done it, then you can estimate the reflectance from radius. This exercise also you have done. That means you have the reflectance of a pixel in a band depending upon certain characteristics and solar zenith angle. And one of the key issues you will face, or probably you have done this exercise, is the influence of slope on incoming solar radiation. So that is where bidirectional reflective function come into place, because the relative position because of the incoming solar radiation will significantly change because of relative position and orientation of ground. And even though incoming solar radiation from Earth, sun is the same, but depends upon the local illumination angle, incoming solar radiation will change. And we will see that in this picture is that if we take the standard incoming solar radiation, which is perpendicular to sun and which is taken above the atmosphere, which is called exoatmospheric incoming solar radiation, then you can see that the reflectance and direction and slope, it can significantly change. So it depends upon which direction it is sloping and how much is the angle of slope. Depending upon that, reflectance can either very high reflectance or very low. So we don't want this kind of error in our result. So one of the key advantage in this, that whatever exercises you have done, you don't have to do if you are using NDSI. That is advantage. So your calculations become much simpler. So if you can look into that, if it is a 10-degree slope and it is northern facing, then you have reflectance, which is 0.59. If it is south facing, 0.85, east facing, 0.79, and west facing, 0.62. So that is the problem. That means it depends upon the orientation and angle. And if you keep on changing angle, it also keep on changing. So it's a question of, and you can see here, it is more than one if it is south facing and it is a slope is very high. So that is the problem, and this problem can be overcome by cosine correction, no doubt about that, but there's additional efforts are needed to do it. But if you use the NDSI, then this is really because it is a whatever error because of the orientation, they cancel each other because we are using the ratio between band 2 and band 5. We are taking the ratio, so they cancel each other, and NDSI value is not influenced because of the local illumination. That makes the observation much more simpler and easy to do it. So that you can see here how NDSI is now for fresh snow, refrozen snow, high wet snow. So all those things you can see here, and you can do this thing, and then you can do a standard scatter plot where you can do you have a NDSI value and then plotted at the reflectance. So you can see here that one of the you have this is a snow over here, and you have snow under shadow. So what is really happening is that when the first or second slide, when I show you, it is very difficult for you to identify snow under shadow if you are using the reflectors as the only characteristic. But if you convert the reflectance into NDSI, then it is possible for you to identify snow under shadow, essentially because sweet as well as visible green band also has a low reflectance. So because of that, you have a NDSI, which is a proper NDSI you get. But also, as we have seen in earlier slide, you have difficulty in identifying identification of uh, uh, water from snow, whether it is in shadow or whether it is in snow. You can really misclassify a water pixel as a snow pixel. The key question is now that what should be the threshold? So there are two principles on which you can think whether you want to underestimate the snow or you want to overestimate the snow. You can see here in now, when it comes to this boundary, which 0.4 I have put, cloud is very close and the fog is very close. So if you shift this side a little bit, it's quite possible some of the cloud pixel can be identified as a snow pixel. So key question is how we are going to have a threshold value. There are a lot of discussions on this. And another issue is in this is how there is a mixed vegetation. That means if there is a significant if there is a snow which is below the vegetation, then how we can identify snow pixel. So suppose you have vegetation mix where 1/4 of pixel, you can see here, the top graph which represents the snow, there is no vegetation. Then this is a pixel, which is a mixed pixel, which is a 1/4 of vegetation. Then this is a 1/3, this is 3/4 of vegetation, and this is a full vegetation. So you can see here that even if 1/4 of vegetation is there, then still you can have this the red edge here you can see, and then what will happen to the NDSI? So if it is a full vegetation anyway, it is 0.13, which is below, then even if 3/4 of vegetation, then NDSI is much higher. So, and 1/4 is also very high, and mixed vegetation, 1/4 vegetation is. So what it means that the most of the Himalayan forest, which is mostly deciduous forest when you go, or alpine forest when you go into the high mountains, most probably we will able to identify snow, which is at below the vegetation cover, if it is the alpine kind of forest. So now key question for us is how do we estimate the threshold value? So one of the principles for this is if you use the sensitivity analysis. That means how sensitive is this? So suppose you take a geographical area which by visual analysis, you know, it is 100% snow cover. If you take that geographical area and you start shifting, changing the threshold value to find out what is its sensitivity. So if it is you change it from 0 to 1, and then percent change in area, you plot it, and it is against the NDSI value. Yeah. So it will change 1 to 2. If we change, there is no significant change in percent area of snow. If you take 2 to 3, there is also no significant change. It is then if you take 3 to 4, there is no significant change in takes place. And if you take 0.4 to 0.5, it looks like some area you are starting to lose. If you take from 0.5 to 0.6, then significant, some more area lose, and then it really collapses. So if you really want to be a conservative estimate, and if you don't mind a little bit overestimation of snow cover, then maybe zero point 0.4 is the value. You can see that once you change 0.4 to 0.5, if you take the blue, which is the mean, you can see there is some reduction in snow cover is taking. So that is also entire area is a snow cover. We know that. And because we change 0.0 to 1, 1.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4, there is no change in snow cover. That means there were no pixels. We are not able to remove any snow pixel from there. That's the idea. I hope I make it very clear. So you can use this threshold value to, and then do the sensitivity analysis and do the 0.4. Some people have used different value. You can do that also, provided difficulty will come when there are various reasons because of the if your calibration is not proper of satellite sensor or some other reasons, it's quite possible that you may not be able to get 0.4 in. So when you run this algorithm and you do that, so you can have a clouds which you may not identify snow, and you have under mountain shadows you can identify some of the snow which is under mountain shadow, you can identify over here. So, but it is not solving. Some of the issues still lingers because if you take this as a here you take as a cloud, this is showing as a non-snow pixel. It is correct that it is a cloud pixel, and in this particular case, it is correctly. But it has not resolved our problem. Our problem is not correctly identified cloud, but our problem is to identify whether there is a snow below the cloud or not. That is the problem. So many times people give huge emphasis in identification of cloud, whether there is a cloud or there is no cloud. It is okay, you need to avoid misclassification, but still problem remains very. What happens if there is we identify any pixel as a cloud pixel, and below that, if there is a snow and we say it is a non-snow, then you have introduced a lot of error in your estimate. That's the another problem we need to address. So how do we address all these problems is some of now creative thinking will come into the picture when we have this problem. So what are those creative pixels? So you take band 2 and 4, 2 and 5 in ABIS. Even band 2 is a green band, band 5 is a sphere band. Convert it into the reflectance image. And once you have reflectance image, you convert it into the normalized difference known. So satellite data is acquired every 5 days. That is why you have advantage. So what essentially you can do is you take First, if it is a greater than 0.4, that is a threshold value you have done. Then you take that and straight away say it is a snow pixel, because on a given date, whatever you have taken, you have do it. So when you have that snow, that pixel is identified as a snow pixel, and it is that pixel is removed from reanalysis. Now you have zero point 0.4 to less than 0.4, greater than 0 or greater than. So you essentially, it means that you have two pixels, two category of pixel. One of that is a cloud pixel, or there are other pixels within that, less than our, that we have seen it is less than. So if you really want to know, sometimes people want to know that it doesn't matter whether there is a cloud or whether there is a snow. You just give me at the interval of 5 days. So you can really give snow and cloud map. So that means it means snow and cloud. So this is one product which is generated by using ABIPS data. So if you are not interested in cloud, you really don't want that. And then you take this pixel, which is a less than 0.4 together, and you go n minus 5. That means if it is done on 10 pixel, then you go on 10th April, then you go to 5th April. So you again take satellite images, then do the NDSI image, and you apply the filter reflectance of band 4 into this, and you identify whichever is a snow pixel and whichever is non-snow pixel. So whatever identified as a snow pixel, then it goes out as another. So it goes out as a 10 daily snow snow cover. Then again, there will be some non-snow pixel. You go 5 days after. That means you go to 15th of April. Again, you follow it, and then you identify. So what it means is, by analyzing 3 satellite images, you identify pixel, which is a snow pixel. And so what essentially it means, that it means this algorithm has 2 things. One thing is, it is giving you maximum snow cover for that 10 days. And once we identified any pixel as a snow pixel in this process, you are not reanalyzing this thing. That means if you have done some mistake in doing that, that is carried forward. So that is the limitation of this algorithm. So you get the 10. So this algorithm is still used by ISRO. So if you are downloading snow cover products from MOSDAQ site of Space Application Center, if I'm not wrong, and if they have not modified it, it is still this product. In this process, these products are generated. And it is still available. This was originally developed by me when I was in ISRO in 2005 and 6 timeframe, and it is still being used because sensor characteristics have not changed. Another thing you can use is, you can apply the basin mask over that, and basin wise, you can generate the 10 daily snow cover mask. So one of the key difficulties, as I have told you, is originally we thought it may not be there, but when it is another one thing to develop this algorithm for 1 to 5 satellite images, and we start analyzing thousands of images. That means every 5 days, and then there is a huge Himalayan mountain range from Afghanistan until to Burma. If you want to cover all regions, the thousands of satellite images are to be analyzed. And it produces a very different nature of issue. So we didn't realize that originally what happens is that there's a lot of clouds which you can identify, but there are some clouds like here, which is ice clouds, which you cannot identify because it has a similar reflectance characteristic. And your product will be really have a lot of errors into it. That's the issue. And there is also issue about this cloud, which you can identify correctly. But the idea is within that 10 days time frame, the pixel which was once covered by cloud, at least out of these three images, one images will be moved because it is a period of 10 days. So that was the idea. Most of the time it works, sometimes it may not work. So this is the idea was done, and the monitoring of seasonal snow was done for numerous sub-basins between 2005 to 9, and I think still it is continued in Ganga Basin, Satluj Basin, Chenab, Indus, Tista, and Brahmaputra Basin. This is how this snow cover monitoring is being done throughout the. Another question comes in, once you have algorithm, you want to validate that algorithm. How you are going to validate that algorithm? There could be a simple way to do that, but I don't think this, but this is anyway is done is, you want to validate, say you go to some of the observatories they are there, whether you take the snow and avalanche study establishment, or there are Bhakra Bias Management Board, there are observatories where they measure the snow thickness or weather. So you, from them, you take the coordinates of their observatory and see that whether there is a standing snow or not. So it is a large geographical area, then you can match it. So, and then the cloud cover, you cannot match it. So you can see that very high accuracies will come if you remove the cloud, whether snow and non-snow, you can vary. But this is one way of doing it, or you can develop an algorithm which is a completely different set. That means you can, validation of algorithm can be done by using opportunistic conditions. So you wait and you have a large geographical area, which is snow. So you wait till the major snowstorms come into this region. So when the major snowstorm comes and when it dumps significant amount of snow, and then you take the nearest satellite images immediately after, because you get satellite images every 5 days. So once the snowstorm vanishes, within a couple of days, you might get your good satellite. You identify geographical area, which you have done earlier also. With your past experience that this much area is a significant, receives a lot of snow, and it is almost all 100% on snow, under seasonal snow. What you do is, for that geographical area, you do the classification when there was no snow, and you identify pixel, whether there will be some glaciers and ice, then barren land, sparse vegetation, and dense vegetation. That is how you can do. So you know the total pixel, and the moment snowstorm goes, you again identified how many pixels you can identify the snow, and then you know how many pixels are there, and you get the accuracy. So accuracy is very high. If it is 99%, if it is a snow and ice, 98% is barren land, then 97% is sparse vegetation, and 96%, 95.8%. So this is how you can do the validation. But even doing all these things, it is possible for you to get some issues because of cloud cover. So at the end of the day, when we're doing this algorithm, and we realize there's a lot of melting will taking place in this region, which is not related, because if you have a snow, the change in snow cover over a period of time is not related, but it is only related due to the ice cloud. So eventually, so what is really we did is we visually analyze satellite image and make sure that there is no ice cloud, and then we put it into the put into the loop, and that is how it was done. And you can see how the snow cover accumulation here. You can see that snow accumulation and ablation pattern in Bhaga Basin, which is very high altitude basin. and the Ravi Basin, which is relatively low altitude basin, suggesting how snow is melting in the middle of winter and how snow is stabilized in the middle of winter. So this is how you can do the analysis and do. So at the end, before conclusion, I would like to bring some of these um, issues which there is scope for you to do, and there's a lot of work has already been done in this. That so first you should think that why we cannot use the digital number, uh, and then why do reflectors change on different slope and orientation? You have done that exercise. And why they say do not change on different slope and orientation? Why we should use normalized difference than ordinary ratio? You remember why that you try and do a little bit exercise by your own. Why does cloud give error in snow cover estimation? Can we use the temperature threshold to improve the accuracies? And can we estimate snow under mountain shadow by using NDSI technique? So can we estimate snow under vegetation? So these are the questions you should ask yourself, and on the basis of the lecture I have given today, you can try to answer this question to yourself, which is not necessary for you to send it to us, but you should do it yourself so that you can get the clarity on what lecture I have given today. So with this, I would like to thank you all, and if